Okay, so now let's talk a little bit about data pre-processing, right? So the activation function, we designed this as part of our network. Now we want to train the network, and we have our input data that we want to start training from. So generally, we want to always pre-process the data, and this is something that you've probably seen before in machine learning classes if you've taken those. And some standard types of pre-processing are you take your original data, and you want to zero mean them, and then you probably want to also normalize them, right? So normalized by this standard deviation. And so why do we want to do this? For zero centering, you can remember earlier that we talked about, right, when all of the inputs are positive, for example, then we get all of our gradients on the weights to be positive, and we get this basically suboptimal optimization. And in general, even if it's not, all zero or all negative, any sort of bias will still cause this type of problem. And so then in terms of normalizing the data, this is basically, you want to normalize data typically in machine learning problems, right, so that all features are in the same range and so that they contribute equally. In practice, since for images, and which is what we're dealing with in this course here for the most part, we do the zero centering, but in practice, we don't actually normalize the pixel values so much because generally for images, right, at each location, you already have relatively comparable scale and distribution, and so we don't really need to normalize so much compared to, more general machine learning problems where you might have different features that are very different and of very different scales. And in machine learning, you might also see more complicated things like PCA or whitening, but again, with images, we typically just stick with the zero mean, and we don't do the normalization, and we also don't do some of these more complicated pre-processing. And one reason for this is generally with images, we don't really want to take all of our input, let's say pixel values, and project this onto a lower dimensional space of new kinds of features that we're dealing with. We typically just want to apply convolutional networks spatially, right, and have our spatial structure over the original image. So the question is, we do this pre-processing in the training phase. Do we also do the same kind of thing in the test phase? And the answer is yes. So let me just move to the next slide here. Right, so in general, on the training phase is where we determine our, let's say, mean, and then we apply this exact same mean to the test data. Right, so we'll normalize by the same empirical mean from the training data. Okay, so to summarize, basically for images, right, we typically just do the zero mean pre-processing, and we can subtract either the entire mean image. So from the training data, you compute the mean image, which will be the same size as each image. So for example, 32 by 32 by 3, you'll get this array of numbers, and then you subtract that from each image that you're about to pass through the network, and you'll do the same thing at test time for this array that you determined at training time. In practice, we can also, for some networks, we also do this by just subtracting a per channel mean. And so instead of having an entire mean image that we're going to zero center by, we just take the mean by channel. And this is just because it turns out that it was similar enough across the whole image. It didn't make such a big difference to subtract the mean image versus just a per channel value. And this is easier to just pass around and deal with. So you'll see this as well, for example, in a VGG network, which is a network that came after AlexNet that we'll talk about later. Okay, so there are two questions. The first is, what's a channel in this case when we are subtracting a per channel mean? And this is RGB, right? So our images are typically, for example, 32 by 32 by 3, so width, height, each of 32. And our depth, we have 3 channels, RGB, and so we'll have one mean for the red channel, one mean for green, one for blue. Okay, so the question is, when we're subtracting the mean image, what is the mean taken over? And the mean is taken over all of your training images, right? So you'll take all of your training images and just compute the mean of all of those. Yeah, so the question is, we do this for the entire training set once before we start training. We don't do this per batch, and yeah, that's exactly correct. So we just want to have a good sample, right? An empirical mean that we have, and so if you take it per batch, if you're sampling, reasonable batches, it should be basically you should be getting the same values anyways for the mean, and so it's more efficient and easier. Just do this once at the beginning. You might not even have to really take it over the entire training data. You could also just sample enough training images to get a good estimate of your mean. So the question is, does the data preprocessing solve the sigmoid problem? So the data preprocessing is doing zero mean, right? And we talked about how sigmoid, we want to have zero mean. And so it does solve this for the first layer that we pass it through, right? So now our inputs to the first layer of our network is going to be zero mean, but we'll see later on that we're actually going to have this problem come up in much worse and greater form as we have deep networks. You're going to get a lot of non-zero mean problems later on, and so in this case, this is not going to be sufficient. So this only helps at the first layer of your network. Okay, so now let's talk about how do we want to initialize the weights of our network. Right, so we have, let's say, a standard two-layer neural network, and we have all of these weights that we want to learn, but we have to start them with some value, right? And then we're going to update them using our gradient updates from there. So first question, what happens when we use an initialization of w equals 0? We just set all of the parameters to be 0. What's the problem with this? All the neurons will do the same thing, right? So they might not all be dead. Depending on your input value, you could be in any regime of your neurons, so they might not be dead. But the key thing is that they will all do the same thing, right? So since your weights are 0, given an input, every neuron is going to have this same operation basically on top of your inputs. And so since they're all going to output the same thing, they're also all going to get the same gradient, right? And so because of that, they're all going to update in the same way. And now you're just going to get all neurons that are exactly the same, right? Which is not what you want. You want the neurons to learn different things. And so that's the problem when you initialize everything equally. And there's basically no symmetry breaking here. So the question is, because the gradient also depends on our loss, won't one backprop differently compared to the other? So so in the last layer, like, yes, you do have basically some of this, the gradients will get the same, we'll get different loss, right, for each specific neuron based on which class it was connected to. But if you look at all the neurons generally throughout your network, like you're going to, you basically have a lot of these neurons that are connected in exactly the same way. They have the same updates, and it's basically going to be a problem. Okay, so the first idea that we can have to try and improve upon this is to set all of the weights to be small random numbers that we can sample from a distribution. So in this case, we're going to sample from basically a standard Gaussian, but we're going to scale it, right, so that the standard deviation is actually 1e negative 2, 0.01. And so this gives us many small random weights. And so this does work okay for small networks, right? Now we've broken the symmetry. But there's going to be problems with deeper networks. So here, this is basically an experiment that we can do, where let's take a deeper network. So in this case, let's initialize a 10-layer neural network to have 500 neurons in each of these 10 layers. Okay, we'll use tanh nonlinearities in this case, and we'll initialize it with small random numbers, as we described in the last slide. So here we're going to basically just initialize this network. We have random data that we're going to take, and now let's just pass it through the entire network. And at each layer, look at the statistics of the activations that come out of that layer. And so what we'll see, this is probably a little bit hard to read up top, but if we compute the mean and the standard deviations at each layer, we'll see that at the first layer, this is the means are always around 0. If we look at the outputs from here, right, the mean is always going to be around 0, which makes sense, right? So if we look here, let's see, if we take this, we looked at the dot product of x with w, and then we took the tan h nonlinearity, and then we stored these values. And so because the tan h is centered around 0, this will make sense. And then the standard deviation, however, shrinks, and it quickly collapses to 0, right? And so if we're plotting this, here, this second row of plots here is showing the mean and the standard deviations over time per layer. And then in the bottom, the sequence of plots is showing for each of our layers what's the distribution of the activations that we have. And so we can see that at the first layer, we still have a reasonable Gaussian-looking thing. It's a nice distribution. But the problem is that as we multiply by this w, these small numbers at each layer, this quickly shrinks and collapses all of these values, right, as we multiply this over and over again. And so by the end, we get all of these zeros, right, which is not what we want, right? So we get all the activations become 0. And so now let's think about the backward pass. So if we do a backward pass now, assuming this was our forward pass, and now we want to compute our gradients. So first, what does the gradients look like on the weights? Okay, so if we think about this, we have our input values are very small at each layer, right? Because they've all collapsed to this near 0. And then now at each layer, we have our upstream gradient flowing down. And then in order to get the gradient on the weights, remember it's our upstream gradient times our local gradient, which for this dot product, we're doing w times x, is just basically going to be x, which is our inputs, right? So it's again the similar kind of problem that we saw earlier, where now so here because x is small, our weights are getting a very small gradient and they're basically not updating, right? So this is a way that you can basically try and think about the effect of gradient flows through your networks, right? You can always think about what the forward pass is doing, and then think about what's happening as you have gradient flows coming down and different types of inputs, what the effect of this actually is on our weights and the gradients on them. And so also, if we think about, right, what's the gradient that's going to be flowing back from each layer as we're chaining all these gradients, right? So this is going to be the flip thing where we have now the gradient flowing back is our upstream gradient times, in this case, the local gradient is w, right, on our input x. And so again, because this is the dot product. And so now actually going backwards at each layer, we're basically doing a multiplication of the upstream gradient by our weights in order to get the next gradient flowing downwards. And so because here we're multiplying by w over and over again, you're getting basically the same phenomenon as we had in the forward pass, where everything is getting smaller and smaller, and now the upstream gradients are collapsing to 0 as well. Yeah, so I guess upstream and downstream can be interpreted differently depending on if you're going forward and backwards. But in this case, we're going backwards, right? We're doing back propagation. And so upstream is the gradient flowing. You can think of a flow from your loss all the way back to your inputs. And so upstream is what came from what you've already done, flowing, down into your current node, right? So we're flowing downwards, and what we get coming into the node through backprop is coming from upstream. Okay, so now let's think about what happens when, we saw that this was a problem when our weights were pretty small, right? So we can think about, well, what if we just try and solve this by making our weights big? So let's sample from this standard Gaussian, now with standard deviation 1 instead of 0.01. Or if our weights are now all big, right, and we're passing them, and we're taking these outputs of W times X and passing them through tan H nonlinearities. Remember, we were talking about what happens at different values of inputs to tan H. So what's the problem? Okay, so yeah, so I heard that it's going to be saturated. So that's right. Basically now, right, because our weights are going to be big, we're going to always be at saturated regimes of either very negative or very positive of the tan H. And so in practice, what you're going to get here is now, right, if we look at the distribution of the activations at each of the layers here on the bottom, they're going to be all basically -1 or +1. Right, and so this will have the problem that we talked about with the tan H earlier when they're saturated, that all the gradients will be 0 and our weights are not updating. So basically, it's really hard to get your weight initialization right? When it's too small, they all collapse. When it's too large, they saturate. So there's been some work in trying to figure out, well, what's the proper way to initialize these weights? And so one kind of good rule of thumb that you can use is the Xavier initialization. And so this is from this paper by Glorot in 2010. And so what this formula is if we look at W up here, right, we can see that we want to initialize them to these, we sample from our standard Gaussian, and then we're going to scale by the number of inputs that we have. And you can go through the math, I think it's in the lecture notes as well as in this paper, of exactly how this works out. But basically, the way we do it is we specify that we want the variance of the input to be the same as the variance of the output. And then if you derive what the weights should be, you'll get this formula. And intuitively, what this kind of means is that if you have a small number of inputs, right, then we're going to divide by this smaller number and get larger weights. And we need larger weights because with small inputs and you're multiplying each of these by a weight, you need larger weights to get the same larger variance at output, and kind of vice versa for if we have many inputs, then we want smaller weights in order to get the same spread at the output. So you can look at the notes for more details about this. And so basically now if we want to have a unit Gaussian, right, as input to each layer, we can use this kind of initialization to, at training time, be able to initialize this so that there is approximately a unit Gaussian at each layer. Okay, and so one thing this does assume, though, is that it assumes that there's linear activations, and so it assumes that we are in the activation, in the active region of a tan H, for example. And so again, you can look at the notes to really try and understand this derivation. But the problem is that this breaks when you use something like a ReLU, right? And so with the ReLU, what happens is that because it's killing half of your units, right, it's setting approximately half of them to 0 at each time, it's actually having the variance that you get out of this. And so now if you just make the same assumptions as your derivation earlier, you won't actually get the right variance coming out. It's going to be too small. And so what you see is, again, this kind of phenomenon as the distribution starts collapsing. In this case, you get more and more peak towards 0 and more units deactivated. And the way to address this was something that has been pointed out in some papers, which is that you can try and account for this with an extra divided by 2, right? So now you're basically adjusting for the fact that half the neurons get killed, and so your kind of equivalent input has actually half these number of inputs. And so if you just add this divide by 2 factor in, this works much better, and you can see that the distributions are pretty good throughout all layers of the network. And so in practice, this has been really important actually for training these types of little things to really pay attention to how your weights are, make a big difference. And so, for example, you'll see in some papers that this actually is the difference between the network, even training at all and performing well versus nothing happening. So proper initialization is still an active area of research, and so if you're interested in this, you can look at a lot of these papers and resources. A good general rule of thumb is basically use the Xavier initialization to start with, and then you can also think about some of these other kinds of methods.
이번 시간에는 데이터 프리프로세싱에 대해서 다루도록 하겠습니다. 데이터의 프리프로세싱은 머신러닝에서도 언급한 바가 있는데 이번 시간에는 스텝 1에서 오리지널 데이터를 제로 센터 데이터로 바꾸고 이를 다시 노멀라이즈 데이터로 바꾸는 것에 대해서 이야기하겠습니다. 제로 센터가 뉴럴 네트워크의 프리프로세싱에서 필요한 이유는 옵티마이제이션에서의 효율성 때문입니다. 우리는 지난 시간에 뉴런의 인풋이 항상 포지티브인 경우에 W의 그라디언트가 항상 포지티브나 항상 네거티브가 된다고 배웠습니다. 만일 우리가 제로민 데이터를 갖게 되면 이러한 문제를 피할 수 있게 됩니다. 한편 데이터를 노멀라이즈 하는 것은 스탠다드 데비에이션으로 나눠줌으로써 모든 피처가 같은 레인지에 있도록 하는 것입니다. 머신러닝에는 프리프로세싱 기법으로 PCA나 화이트닝 같은 것을 볼 수 있지만 이미지 프로세싱에서는 이러한 것들을 잘 사용하지 않습니다. 실제로는 이미지에서 평균값을 구해서 빼줌으로써 제로 센터링을 하도록 합니다. 알렉슨의 경우에는 32 곱하기 32 곱하기 3 어레이로부터 민 이미지를 구해서 모든 픽셀에서 이 값을 빼주도록 합니다. 한편 의지진넷에서는 채널별로 평균값을 따르고 하여 빼줌으로써 제로 센터링을 구현하도록 합니다. 다음은 Weight Initialization, 초기화에 대해서 논의하도록 하겠습니다. 첫 번째 질문은 만일의 웨이트의 초기값이 모두 0일 경우 어떻게 동작하는가입니다. 레이어들은 매우 비효율적으로 동작합니다. 우리가 원하는 것은 서로 다른 웨이트 값을 가지면서 서로 다른 것들을 학습하도록 하는 것입니다. 첫 번째 아이디어는 작은 랜덤 넘버로 초기화를 하는 것입니다. 가우시안 디스트리뷰션으로 제로 평균과 100분의 1의 스탠다드 데비에이션을 가지도록 합니다. 이 경우에 작은 네트워크에서는 어느 정도 동작하지만 디퍼 네트워크에서는 문제점들이 있습니다. 컴퓨터 시뮬레이션을 통해서 직접 동작시켜 보도록 하겠습니다. 이 경우에 10개의 레이어가 있고 각 레이어마다 500개의 뉴런들이 있습니다. 웨이트의 초기값을 민을 0으로 스탠다드 데비에이션을 0.01로 했을 때 시뮬레이션의 결과입니다. 트레이닝을 한 결과 첫 번째 레이어는 아직 가우시안 디스트리뷰션 모양을 유지하고 있지만 나머지 레이어들은 민과 스탠다드 데비에이션이 모두 0에 가깝게 되었습니다. 이렇게 되면 모든 액티베이션 값들이 0에 가깝게 됩니다. 이러한 것은 바람직하지 않은 현상입니다. 웨이트의 초기값이 너무 작았기 때문에 이러한 현상이 발생했습니다. 이번에는 웨이트의 스탠다드 데비에이션 값을 1로 크게 키워보겠습니다. 이번에는 모든 뉴런들은 완전히 세츄레이션 되어서 마이너스 1이나 1값만을 갖게 되었습니다. 이 경우에 그라디언트는 모두 제로 값을 갖게 됩니다. 이 역시 우리가 원하는 결과가 아닙니다. 따라서 웨이트 이니셜라이제이션은 매우 중요하며 스탠다드 데비에이션은 0.01부터 1 사이에 적절한 값을 가져야 된다는 것을 알 수 있습니다. Xavier Initialization은 이러한 웨이트의 초기값을 적절히 줄 수 있도록 고안되었습니다. 웨이트의 초기값을 계산할 때 이전 노드 개수와 다음 노드의 개수를 활용하는 방법입니다. 시뮬레이션 결과 대부분의 웨이트들이 0이 되거나 세츄레이션 되는 것 없이 적절한 분포를 갖는 것을 볼 수 있습니다. 그러나 세비어 초기화 역시 렐로를 사용할 경우 알고리즘이 브레이크 되는 것을 볼 수 있습니다. 이처럼 웨이트의 초기화는 아직도 많은 연구가 필요한 분야입니다.